Lesson on logic gates unit. Before we start, here's the table of contents. Here's the timestamp and here's the content. From 0 to 1 hour and 9 minutes 50 seconds, it talks about truth tables and functions of each logic gate. From 1 hour 9 minutes 52 seconds to 1 hour 49 minutes 58 seconds, it talks about Boolean algebra. And lastly, from 1 hour 50 minutes to 2 hours 26 minutes 58 seconds, it talks about half adders and full adders. Hello, my name is Anish Das, and today I will be teaching you how to do logic gates. The first step in learning how to use and do logic gates is to learn how to make a truth table. What is a truth table, you say? A truth table is a table that allows us to solve for the value that's going to be at the end of the logic gates. For instance, in this hello, my name is Anish Das, and today I will be teaching you how to do logic gates. The first step in learning how to use and do logic gates is to learn how to make a truth table. What is a truth table, you say? A truth table is a table that allows us to solve for the value that's going to be at the end of the logic gates. For instance, in this example, there is A, B, and C here. Now, keep in mind that this is a schematic of a random logic gate here. This schematic shows the schematic just shows what the values of A, B, and C will go through. So basically the reason why we use a logic gate is just like how in math how we use algebra to solve for a linear graph or a equation. We use a truth table to solve for schematics like this, so we know what value comes out from here. So what value is here? So let's start by getting the basics. In a truth table, there could be multiple different combinations. There could be one combination, there could be two combinations, there could be three combinations. And what we do is we use the power rule and we use it to the combinations power. What I mean by this is because truth tables use binary number systems, our base will be two. Two is our base. Because two is our base, because 2 is our base, we're going to be multiplying 2 however many times by itself by putting it putting it to exponent. So in this case, there is 3 inputs. So we would do 2 to the power of 3. Sorry, 3, which equals to 8. So what this means is that depending on the number of inputs that are in the schematic, you would have to put it to the power of 2. You would have to put it to the power of 2. What this means is that there's going to be 8 different combinations. There's going to be 8 different there's going to be 8 different combinations, meaning there's going to be 8 different values or variables in the end for the value. And so if there were two inputs, then we would do 2 to the power of 2, which would equal to 4 combinations, which would mean that that a value at the end, the value the value at the end would have four digits. Would have 4 digits. Keep in mind, keep in mind, keep in mind that all of this is done in binary. That is why two is a two is a base for our exponent. All right, now let's move on. Now let's move on to the actual making of the truth table. Now that I've explained to you how the combinations work. So for this, we'll use the example in this page right here. We'll use the example. We'll use the example on this page right here to show you how to make a truth table. Here we see that there's 3 inputs, so we would automatically do the exponent. So we would do 2 to the power of 3 equals 8. So we know that there's 8 combinations, which means value will be 8 digits long. So now from here, what we do is we count from 0 to 7. The reason why we don't count, when we're doing truth tables, we make a table like this. Because there's three inputs, we have a table for each input. We have a table for A, we have a table for B, and we have a table for C. And basically, and the reason why we have A, B, and C is because there's three inputs. As you can see here, there's three inputs here. As you can see here, for the truth table, it's to the power of 3. So we have three inputs here as well. We have three inputs here as well. So what this means is is that we will have to count. So what this basically means is that we'll have to count from 0 to 7. And as I was saying earlier, the reason why we count from 0 to 7 is not 1 to 8 is because when we're doing binary numbers and truth tables, we don't start off as 1, just like in normal math or algebra. Because we're working with numbers, we start off at 0. So we're actually going from 0 to 7. And 0 counts as one whole digit itself. So 0 is 1, 1 is 2, 3 is uh, uh, 3. I mean, no, 0 is 1, 1 is 2, 2 is 3, 3 is 4, 4 is 5, 5 is 6, 6 is 7, 7 is 8. And so in that way, 0 to 7 are actually 8 digits. And so the way we write this down is we go by the multiples of 2, right? So we write 1, 2, and 4. And so depending on whichever way we write, depending on like how many variables there are, that's how we would write it. So right here we have three variables, so it would be 1, 2, and 4. If there were four variables, it would be 1, 2, 4, and 8. It kind of goes by the multiples of 2. uh, it kind of goes by like how much like 2 can multiply by. Like 2 times 1 equals 2, 2 times 2 equals 4, 2 times 4 times 2 times 2 equals 8. So basically, the reason why there's 1, 2, and 4 here is because of the exponent. So 2 to the power of 1, so it starts off at 1 and it continues going. So 2 to the power of 1 would be 2, 2 to the power of 2 would be 4, and 2 to the power of 3 would be 8. So if we had another one right here, let's just name it x. That would represent 2 to the power of 3, and it would be 8. But currently we don't have one. We don't have another value, so we don't need to worry about that. And so now what we're doing is we're writing the zeros and ones as we're doing binary into these slots. So what I mean by this is that we're gonna start off at 0. So all of these will be 0. Then we're gonna have 1. So depending on whatever numbers are here, you have to put the 1 there, as 1 represents, like, the computer is on to represent the value. So in order to represent 1, I would have to put 0, 0, and 1 here, as 1 and 1 equals 1. And now that I have 2, I have to do 0, 1, 0 here. And so that represents like the number it holds. So this represents 0, this represents 1, this represents 2. And you can tell because of the 1 value. The 1 value, whichever the column the 1 value is under, tells you what value it is. For instance, as we go on to 3, we do 0, 1, 1. And this is 3 because over here 2, then over here 1. So 2 plus 1 equals 3. That is why it's 3. As we move on to 4, it becomes 1, 0, 0. As you can see here, it's 4 because it's in this column, as this represents 4. And going back to re-summarize again, the reason why we have 1, 2, and 4 here is because we go up by exponents of 2. So the reason why 2 is here is because 2 to the power of 1 equals to 2. The reason why 4 is here is because 2 to the power of 2 equals to 4. The reason why, if we had a fourth input like x, the reason why it would be 8 is because 2 to the power of 3 would be 8. And we always start off at 1 when we're doing these type of things. So the first column in front of all the other columns will always be 1, as 1 is kind of like the basic value for exponents. So we say. Now that you know how to actually make the now that you know how to actually make the logic gates, let's make the logic gate for this properly. So as I said, we have 8 combinations. So what we would do is, as I said, we have 8 combinations here. So what we would do is, all right, let's actually start the logic gate making now. So as I've already said, we have 3 inputs. So we put 3 inputs right here: A, B, and C. Remember, this represents 1, this is 2, this is 4. Yeah, as I was saying, this represents 1, 2, and 4. So what we do here now is we just fill it in. That's all you need to do. For this part, all you need to do is fill it in. So we know the first number is going to be 0. So 0, 0, 0. And we just fill it in from 0 all the way to 7, as that is equal to as this is equal to 8 combinations slash digits. Next number is 2, so we do 0, 1, 0. Next number is sorry. Next number is 1. My bad. This part here is 1. So next number here is 1. Next number here is 1. So we do 0, 0, 1. Next number is 2, 0, 1, 0. Next number is 3, 0, 1, 1. 2 plus 1 equals 3. Next number is 4, 1, 0, 0. Next number is 5, 1, 0, 1. As 1 here is 4. 1 here is 1. 4 plus 1 equals 4 plus 1 equals 5. 4 plus 1 equals 5. Then the next number is 6, 0, 1, 1, 0, which means that as the 4 plus 2 equals 6, and the last number is 1, 1, 1. As 4 plus 2 plus 1 equals 7. 4 plus 2 plus 1 equals 7. And that's how you do it, really. So the main part of the truth table, which is this part right here, is finished. And your truth table for this part will always look the same, no matter what value, no matter what happens. Your truth table for this part will always look the same, unless there is a different number of inputs. So if there were 4 inputs, your truth table would be much more longer. For instance, if there were 4 inputs, there would if there were like 4 inputs, there would be 16. If there were 3 inputs, there would be if there were I mean yeah, my bad. If there were 3 inputs, there would be 16. So depending on how many inputs you have, you just continue using the 1, 2, and 4 method. As I said, all of this starts off at 1, then it goes by exponents of 2. So 2 times 2 to the power of 1, 2, 4, 2 to the power of 2, 4, 2 to the power of 3, 2 to the power of 2, 4, 2 to the power of 3, 8, and etc. It just continues like that. So you continue putting your truth table like this. So yeah, it'll always almost look the same. And so the way how we use these truth tables is that when we get a schematic, we can go all the way back to the front here. When we get a schematic like this, we will be adding and subtracting the numbers together depending on the gate. I will be teaching you this in a second. But basically, the reason why we use these truth tables, A, B, C, is because then the values that are here, the values here will be added or subtracted to will be added or subtracted to depending on the logic gate. So for instance, there is an and logic gate here. So the values for, and depending on whichever one goes through it first, as you can see, A and B both go through the and logic gate. A and B, would first get multiplied together. Then the rest of them. So in this way, after we've finished writing all I'm just gonna fill it up just so you could like see how it is randomly. I'm just gonna fill it up randomly. So after we fill the main part of the logic gate up, which is here, which is this, we can move on to the next step. We can move on to the next step, which is actually doing the calculations, so we know what type of value comes up next. And in order to do this, you need to know what the seven different logic gates are, and how what each logic gate represents, and how each logic gate works. And I will be showing you how each logic gate works, and how each logic gate is represented through truth tables and what they look like. But before I do that, I want to show you that that when we're making these truth tables, after we filled them out, I'm just filling them out. So I'm just yeah, I'm just filling them out randomly. After we fill them out, depending on the logic gates that's there and how it is placed, we were to do it. So what I mean by this is right here, there is A and B here, as I've said. That would mean you multiply the values of A and B here, and so we just do prop multiplication between the values of A and B. So 0 times 0 equals 0, 1 times 1 equals 1. Just keep in mind that these right here, I, I just wrote them. I just wrote them so I could show you what I mean, like, and what the next step is when it comes to these truth tables. 1 times 1 equals 1 here. 1 times 0 equals 0. 1 times 0 equals 0. So in that way, whatever logic gate comes next, you do the function of that logic gate, and you look at which two inputs are going in. For instance, for this logic gate here, which is known as an OR logic gate, both the B and the C inputs are going in. So you would basically just add B and C together. So you would basically just add B and C together in the next one. B and C, you just add them. So it's same values apply. 1 plus 0 equals 1, 1 plus 1 equals, and we don't write 2 here. When we're adding, which I will explain to you later on when I'm actually explaining you the logic gates, it means just one of something else. 1 plus 0 equals 1, then 0 plus 0 equals 0, 0 plus 0 equals 0. That is what I mean by these logic gates. And in the end, you will see that all of these values will come together at a single point, and that single point will result in your answer. So all of these values will come to a single point, and you'll have a long equation like AB plus BC, and they will give you a value, something looking like this. And that value is the answer. That value is the answer. That value is Q. That value is the answer. So basically to summarize, logic gates, to summarize how to make truth tables. Truth tables are just how we solve algebra. Truth tables are a way of solving schematics like this over here, and we use binary numbers to do that. And because we use binary numbers to do that, we use the base of 2, and depending on however much inputs there are, whether there's 1, 2, or 3 inputs, we put it to the value of 2, and it gives us the amount of combination. And as I've said, the combination represents how long the value will be and how much digits the value will have. And after we found a combination, we just depending on how many inputs there are, we just plug it into a table like this, and we just put the numbers in. And as I've explained, we put the numbers in depending on what each column represents. Remember, the first column right here will always be 1, and then the next columns after this will be exponent of 2. So 2 to the power of 1 equals 2, 2 to the power of 2 equals 4, as I've explained earlier. And once we've finished filling up the actual table, depending on our amount of combinations, and depending on our amount of combinations, we just continue adding or subtracting, no, adding or multiplying the numbers together to get our final equation slash value, which would represent the value over here, as whatever as in order and which would represent the value over there, which we would get by adding or subtracting the values together, as you can see over here. And you figure out which values to add or subtract together, or add together by seeing what truth tables are what truth tables are in place, and what two values go into the truth table. That is why we add A and B in the first one, and B and C in the first one. Why? Because as you can see here, A and B go into this and truth table, which is known to multiply, and B and C go into this and truth table here, which is known to multiply. That is why in my truth table over here, I do A and B and C to show you that these two truth table to show you that we first multiply A and B, then then multiply B and C, as we still have laws to follow. We cannot combine them yet. And then in the end, we can finally combine them over here after everything's done, as all of these schematics will end up giving you a single answer, as all of these schematics end up combining all of the logic gates values together to give you a single algebraic, I mean single binary number, which would be Q. So now that you know why we use truth tables, kind of like how similarly how we use algebra to solve our things. So now that you know why we use truth tables, as we use truth tables to solve schematics like this, to solve schematics like this, and like and yeah, we use truth table to solve schematics like this, and we use the table to actually like do solve the equation by depending on what equation there is. For instance, AB we do first because AB is shown here. Let me teach you what the actual logic gates are. As in order to even use a truth table to solve a schematic like this, you would need to know what each logic gate does. For instance, if you don't know what this here represents, you won't know what function to do. You won't know whether you have to add, whether you have to invert, or whether you have to multiply. If you don't know what logic gate there is, and if you don't know what function to do, you would not be able to do it, as you would not know what to do here. You would not know whether to add the A or B or to multiply the A or B. You need to know what the actual function of the logic gate is in order to move on to adding or subtracting, and and finally and ultimately getting a value like this to for in the end, for like equation like this to get your value in the end. But now I'm gonna teach you what the actual logic gates are. The first logic gate I would like to introduce you to is the inverter logic gate. Now, this logic gate looks something like that. And what this logic gate does is it inverts your value. Now that we know how to make truth tables, we can use it. I can use a truth table to explain to you what this gate does. Now, now you see that there's one input here. So we would do 2 to the power of 1 equals, you guessed it correct, 2. There would be two combinations, so meaning there would be two digits, meaning meaning we would count to 2. So we would, and that makes proper sense, because when we're actually making the truth table, all we're gonna need is one value, and that's gonna represent 1. As we're only gonna have two digits, and we're only counting up, we're only counting up to 1. As remember, 0 represents one digit, so we would just do 0 and 1. And here there is two digits, and here when we did it, there's two digits, as there's only one input. As there's only one input. And so let me show you what this does. So basically, just like how in math there's symbols like to show addition, multiplication, division. The symbol for a not gate, which is what this is called, for a not gate, what this is called a not gate. I'll just uh, I'll just put a text box so you guys can see properly. As you can see, this is called a not. Yes, this is called a not gate. And so the symbol for not gate is either a explanation mark, is either a ex, exclamation mark, or a little underline on the top of the variable. So I could either write it as explanation mark A, to represent the not, or I could write it as a not with a little dash over it. Let me erase these things here so you can see properly. So this is what we would use. This is what we this is what it would look like. And so basically what this gate does is it reverses the value. What I mean by it reverses the value is the a here, the a here would have a value of 0 and 1. As remember, when we have as I said I said earlier that we're counting from whatever we're counting from 0 to whatever number there is depending on the number of digits here, depending on the number of digits here. When the input is put into the not gate, it inverts the input. So right here, because we're counting up to 2, we're gonna have only have two numbers here. We're only gonna have two digits here. It would take the 0 and turn it to a 1. It would take the 1 and turn it to a 0. So basically, what the not gate does, I'll write it out for you. So what the not gate does is it converts the value into its opposite. The not gate converts the value into its opposite. So what this means is that if there was a as what this means is that as you can see here, because there's a 0 here, it turns into a 1. It turns the 0 into the opposite of what it already is. If there's a 1 here, it turns it to the opposite of 1, so it would be 0. So so 1 represents on and 0 represents off, as you've already learned in binary. So if the machine or the signal was off, if the signal was off, it goes through a not gate, and it turns on. If the signal was on, it goes through a not gate and it turns off. That that is what a not gate is. This is the one of 7 gates. The next gate I would like to talk about is the AND gate. Next up is the not AND gate. As you can see, the AND gate has 2 inputs. So as you read here, not gate is the only gate with 1 input, as it only inverts the value. All other types of gate have at least 2 values to add, to have at least two inputs. That's what I meant to say. All other have at least 2 inputs to add, multiply, and etc. So as you can see here for the NOT gate, this is the only gate with one input. While for all other gates like the AND gate, for all other gates other than the NOT gate, they all have 2 or more inputs. They all have 2 or more inputs, as you need 2 inputs to add, subtract, and etc. For an AND gate, it's basically multiplication. You are multiplying multiplying the values here. So here, I'll show you it in a truth table to figure out what this means. Right now we have 2 inputs, so we would do 2 to the power of 2 to get 4 combination slash digits. So what this would mean is that what this would mean is that we would have to count 0 to 3, as there's 4 digits here. As I've explained in the truth table here, because we only have 2 inputs and we have 4 combinations slash digits, we would have to our truth table would have 4 digits here. And so in order to get the 4 digits, we have to count from 0 to 3, as we always start at 0. And 0 ends up being the first digit, 1 ends up being the second digit, 2 ends up being the third digit, and 3 ends up being the 4 digits. And so there's 4 digits there. And as we remember, the column over here always starts with 1, and the column over here always starts with, and the column on the very right side always starts with 1. And then after that, each one of the columns here represent exponent of 2. So because there's only 1 after b here, we would do 2 to the power of 2, which would be 4. So a represents 4. And so now when we do it, it would be 0 to, no, I mean, my mistake. I meant now that there's a here, it would be 2 to the power of 2, which would 2 to the power of 1, which would represent 2. That is what I meant to say. As the truth table always starts off with 1, and uh, the all the other inputs that come after the first column are all like exponents of they're all exponents of 2. They're all exponents of 2. As they're all exponents of 2. Now we just, as I've explained earlier here, over here. Now let's fill it up. So the first digit would be 0 and 0. Next digit would be 0 and 1, which would represent 1. Next digit would be 2, so 1 0. Next digit would be a 1 and 1. 1 and 1. That's 2 plus 1 equals 3. So basically, what this AND gate does is it multiplies your values together. Let me show you what I mean by this. What I mean by this is that the A and B are being multiplied together. And just like remember that just like how in math you use plus and a plus to show that you're adding and x to show that you're multiplying. Over here to show that you're multiplying, just and for the not gate here you use this exclamation mark or this underline over the letter to show that it's being knotted or inverted, so to say. Here, we just write the variables together. So we would write it as A and B. This shows that the input A and the input B are being multiplied together. And and if the A was already inverted, like for instance, if there was already a inversion before the A, and then they go to a AND gate, we would write it something like A not B, or A over B, to show that A is being inverted first. Then it's being multiplied. So the 0 would turn to 1, the 0 would turn to 1, the 1 would turn to 0, the 1 would turn to 0, then you would multiply it together. But I'm just telling you this so you understand that if there was an inversion beforehand, you don't just do the multiplication together. You first invert the A, or whatever has the not gate on it. In this case, it's A. And then you multiply it together. It's kind of like bed mass, how you follow the order. Here, you follow the order of the schematic from left to right. So that's the, and you will understand this when I actually solve the schematic in the front. So you just multiply A and B together, and you just follow the laws of normal multiplication. 0 times 0 equals 0. 1 times 0 equals 0. 1 times 0 equals 0. 1 times 1 equals 1. So this is what it would look like. That is the AND gate. Moving on, the next gate we have is the OR gate. OR gate. Now keep in mind that all of the gates that we're going to be discussing for this lesson and for grade 10 will only have 2 inputs each. So as you can see here, the truth table here will be almost similar to the truth table here, except only the values will be different. As every single gate has its own function. So here we'll just write out the truth table again. A, B, 0 0, and remember it's two inputs, so 2 to the power of 2 equals 4 combinations, so we're counting up to 0 3, so it'd be 0 0 1 1 0 1 1 0 1 2 3, four digits, 4 combinations. Now Now what does the OR gate do? The OR gate simply just adds them together. Just adds them together. I'll show you right here. And in order to show addition, you would just do A plus B. And let's just say that as you go on, you would have to multiply this A plus B to another gate. For instance, because we already learned how to do the AND gate, I'll just use the AND gate. For instance, let's just say it's A and B going through this OR gate. Sorry, my drawings aren't that well. Going through this OR gate, and they were to be multiplied by, again, B, the same value B. Because if we would add another input like C, if we were to make another input like C over here, we would have to, it would not be 2 to the power of 2, but it would be 2 to the power of 3. And so instead of A B C here, we would have to put A B and then C. And so the amount of combinations would change, the amount of digits was changed as I explained earlier. So I'm just gonna add the same. I'm just gonna add the same input of B. I'm just gonna add the same input of B as we only add another exponent to the two as if there's another input. But because B is the same input here, we always we always we always just keep it the same because B is the same input here, so it's still 2 to the power of 2. And so as I was saying, if we just multiply these, you would just use your regular mathematics skills. This would just look like A plus B bracket times B. As you can see here, we're adding the A and B to first and then multiplying it together. As if we multiplied the B and B, then added the multiplication of B and B and A together, we would not have the same answer as you've probably seen in math and algebra. You would have to do the same thing here. So you would have to first add the A plus B, then do the multiplication, and you would do that by putting into bracket first A plus B, then multiplying it by B. So that is just information that you should know when you're dealing with multiplication, when you're dealing with like stuff. You still follow the laws, and you still follow the laws of BEDMAS and etc. And you still follow the schematic as whatever is on the left is first, and then as we come forward to right, it continues forward and forward. You cannot just interchangeably multiply the numbers. You have to multiply the numbers according to the schematic, or add the numbers according to the schematic. So what A plus B here represents is just the same mass. So 0 plus 0 equals 0, 1 plus 0 equals 0, 1 plus 0 equals 1. So it's just simple math again. 0 plus 0 equals 0, 1 plus 0 equals 1, 1 plus 0 equals 1. Now here is the part that you might not understand, but I'll explain it to you. 1 plus 1 actually equals 1. The reason why 1 plus 1 actually equals 1 is because these are just binary numbers. Because these are binary numbers, we cannot have numbers like 2, 3, 4, 5, 6 anywhere. And when this actual logic gate chip is put into an actual function, put into an actual computer, it doesn't just add up the ones as 2, like 1 plus 1 equals 2, 2 plus 1 equals 3. No, it either sees it as on or off. As when you were learning binary, you know that 1 means on, 0 means off. So basically, what this logic gate does is that if both A and B are on, it just stays on. So that's why we don't add 2 or 3 here, as we're not really adding the numbers. We are adding the numbers, but we don't really get another like value like 2 or 3 here because it's binary, keyword binary, but we get another one. So it's one of another value, or one of something else. This basically means that for this logic gate, if there's a 1 for A, 1 for B, this would mean that this is on. It's not off, it's on. That's basically all it means. So just don't worry about it being equal to 2, 3, or 4. Just know that in a OR gate, 1 plus 1 equals 1 of another thing, which means it's still on. Which means the logic gate is still processing the thing. and and that's a OR gate for you. With this OR gate, let's move on to our next gate. And this gate is one of the final gates there is. As you will see, the next three gates, as there's seven like uh proper or normal gates that we're going to be learning in this lesson. This is one of the last this is one of the last new gates that you will learn. As you will see when I start explaining you to the other gates, you'll just see that there are different variations of it. There are different variations of it. So the XOR gate. Let me first draw out the truth table, then explain to you what the XOR gate is. And as you can see, it has two values again. As you can see again, it has two values. As I said, all other gates will have two or more values. The NOT gate is the only gate with one value here. All right, let's do this. So A and B, and as you know, 2 to the power of 2 equals 4 combinations slash digits. We just fill it up. 2B 0001 1011. One one. So just like how every other gate has its own way of showing, like A plus B, AB, then explanation mark and A XOR though it has the way to show XOR is A plus B, but the plus has a circle over it. So A plus B equals to OR gate, while A plus circle of B equals to XOR gate. Equals to XOR gate. So basically, what an XOR gate does is very similar to an OR gate, except it's just one or the other. What I mean by that is that the XOR gate looks at the two values of A and B, and it one chooses one value or the other, and it's always going to choose the value that's on. For instance, here in AB, none of the values are on, so it'd be 0. But here in AB, B value is on because there's a 1 here, and A value is off because there's a 0 there. That would the XOR gate chooses between one or the other, which means that the XOR gate always gives you a choice always has a choice of choosing of choosing the what do you call it? The choosing the value that's on, which is a 1, or choosing a value that's off, which is a 0. If both of the inputs are off, then it has nothing to choose from. It automatically becomes 0 as both of the values are off. But if one of the values is on, it automatically chooses 1. So here, because one of the values is on and one of the values is off, and it's known as XOR, which means one or the other, we would choose the other value, which would be 1. Same logic applies here. 1 or 0, we would choose one or the other. So we would have 1 here. So for all questions that have 0 0, just know it's one or the other that the XOR is choosing. So and because they're both of them are off, they would be 0. They would be 0. But because it has to choose one or the other, it's always going to choose the value that's on. So if it was presented with a value of A being 0 and B being 1, it would choose the on value. So it end up being 1. As same logic applies here. A is on with a 1, but B is on off with 0. So it would choose A, and so you would write the 1 there. But if both of the values are on 1 and 1, as I said again, XOR means one or the other, the XOR gate sees that both of the values are on, and it cannot choose between on and off. Both of the values are on, so it just ends up choosing off, and it becomes kind of like a short circuit kind of. And so in that way, as you can see, to summarize, the XOR value chooses one or the other. XOR chooses one or the other value. Usually usually the on value if it is presented with if it is presented with both both 0 and 1. But if it's presented only with 0 and 0, it cannot choose 1 because none of the values are on, as none of the values have 1. So it would just end up being 0. While if both of the values are on, it has to choose one or the other. So it's going to choose the other value of 0 as both of them are on. So they end up becoming 0. So so that's how the XOR gate works. It chooses one or the other. So it ends up being 0, 1, 1, 0. That is how the XOR gate works. As I said, that the last three gates would be very similar, but a different variation of the earlier gates that you learned about, right? So this is the different variations. The last one that we've seen are just gates mixed with NOT gates. So you cannot mix a OR gate and the AND gate together. You can't mix a XOR gate or a OR gate together, but you could mix a AND gate and a OR gate together, but you could mix. What I meant is, what you could mix a NOT gate and the AND gate together. You could mix a NOT gate and the OR gate together. You could mix a NOT gate and the XOR gate together. For example, I'll show you an AND gate. As you can see here, you can mix NOT gate together with the other gates. So all other gates that I've said, like the AND gate, the XOR gate, and the OR gate, can be mixed together with the NOT gate, and each one of these gates will have a little circle in front of it to represent that it is combined together with the NOT gate. For instance, in a second you will see all the different variations of it. You can see each these are the different variations of it. These are the last three gates. As you can see, each one of the gates are almost similar slash identical. It's just that they have identical to their parent gates. We could call them that. The OR gate is literally the same as the original OR gate, except there's a circle in front of it. There is a circle in front of it. The XOR gate is similar to the XOR gate, but there's a circle in front of it. Same thing with NAND. This circle just represents that the that the AND gate and the OR gate are combined. So we end up not calling them an AND gate anymore. We end up calling them something with with something starting with an N. So the prefix for these gates, I start with an N. So this AND gate would be called a NAND gate. OR gate would be called a NOR gate. XOR would be called the XNOR gate. As you can see, each of the combined gates have a prefix of N. As you can see, each one of the combined gates literally just have a prefix of N. They literally just each have a prefix of N. That's why they're called a NAND gate, NOR gate, and XOR gate. And what these gates do is exactly the same function. Yeah, you heard it correct. It does exactly the same function as its original gate, except it inverts the value. Remember when we were talking about nor x I mean not gates, and how it inverts the value from 0 to 1 and from 1 to 0, how we were talking about all of this. The combined gates here take the value of the AND gate, take the value of the OR gate, take the value of the XOR gate, and they invert it. Let me show you what I mean with the AND gate, for instance. 0 0. Again, it'll be the same truth table as they all have the same number of inputs. 0 0 1 1 0 1 1. So basically what this means is that, so basically it does the same exact, so we're doing it for an AND gate, yeah? So basically we do the same exact thing. We multiply A and B together. 0 times 0, 0, 0 times 1, 0, 1 times 0, 0, 1 times 1, 1. Except after we multiply them together, because we're doing the AND gate here, we also invert it. So we do A bracket A B, or over it A B. We just don't write A B like this, because that would mean we're inverting A first and then multiplying it. We are not inverting A first. We are multiplying A and B together first, then inverting it. That's why we put the bracket here. Just like in normal math, how we, if there's another, if we were to add this together, we would have, and we want to multiply it first, we wouldn't want to add A and whatever value there is together. We would want to multiply A and B together first before we do anything else with the A and B. So now from here, all the NAND gate does is it reverses the value. So A and B value is 0 0 1, as we have seen it with the AND gate, 0 0 1, 0 0 1. It reverses the value. From 0 0 1, it becomes 1 1 1 0. As we talked about in the NOT gate, it reverses the value from on to off, or off to on. Same rule Same rule applies to the two other gates. They just reverse the value of the XOR and OR gate. That's all they do. They just reverse the value. Here, let me show you. Here's the OR gate. A, B. 0 0 0 1 1 0 1 1. We would add them together to get 0 0. 1 plus 0, 1 plus 0, and 1 of something else, as we've talked about earlier. 1 of something else. All this, NOR gate does is it reverses the value. As you can see, this value is the same as the OR gate. Same as the OR gate. I mean, yeah, same as the OR gate. Just reverses the value, bro. Just reverses the value. So we would remember we have to add the brackets, because we're not just knotting a single variable, we're knotting this whole entire equation together. So we add the brackets to show we do the addition first, then we knot it. Or Uh, we inverse it, which would also look like A plus B. This would now become 0 would become 1, while these would all become 0, as we're just inversing it. same logic would apply to XOR gate. So basically for the XOR gate, right over here, you just reverse the values. So the values for the XOR gate, which becomes XNOR gate, as I've already said here, this becomes a XNOR gate. The name of this is a XNOR gate. Let me just add the names real quick. XOR, I mean, NOR gate. Or, and this is the XNOR gate. And let me just name them right here as I finish naming them. It's the XNOR gate, as we've just discussed. This is the XNOR gate. Basically, this would just be the reversal of this. So instead of 0, 1, 1, 0, which is the obvious, which is the actual function of the XOR gate, the XNOR gate would just reverse the answers as shown over here with the NOR gate and the AND gate. It would just reverse the answers to 1, 0, 0, 1 as it turns off to on and on to off. It will just become 1, 0, 0, 1. So that is how all seven of these. So that is how all seven of these gates work. So this is how all seven of these gates work. Now, the last final thing that we have here is that we have to talk about is how do we solve it? How do we solve it? Now that you know how each gate works and how to use a truth table, I'm going to give you an example and I'm going to solve it. I'm going to solve it. And the example we're going to be solved is the very first equation that I've introduced you. No, very first schematic that I first introduced you, which is this schematic right here. How would I drag this? One sec. And so basically, this is how all seven of these gates work, as I've explained. Now, now we will be using the one schematic and solving it to show you how exactly how a truth table works and how exactly we can use our knowledge on what logic gate does what function to solve the actual schematic and get the actual answer. Now we use our knowledge that we've learned from the logic gates and the truth table to solve it. So as you can see here, we have three. We have three inputs. So we would do 2 to the power of 3, which would give us 8 combinations. That would mean we're counting from 0 to 7, as I explained earlier, and we would have 3 inputs, in which the first column would be 1, the second column would be 2, and the third column would be 4. As the first column always starts with 1, and the columns after that are always the exponents of 2. So 2 to the power of 1, 2, 2 to the power of 2, 4. Let's draw the schematic truth table out. A, B, C. 1, 2, 4. 0, 0, 0. Always starting off with 1. 0, I meant. 0, 0, 1. 0, 1, 0. 0, 1, 1. 1, 1, 0, 0. That's a 4, bro. 1, 0, 1. 1, 1, 0. Then 1, 1, 1, 1. So 0 to 7. Now, in order to solve the schematic, we have to go in order. Just like how in algebra and math, we go in order from left to right and we follow BEDMAS, same rules apply here. What I mean by this is that we go left to right. From the schematic, we start here and then we go left to right, ending here, ending here, ending here. And that is our answer. And so first we have to identify all the gates there are. We know this is a AND gate. This is a OR gate. This is an AND gate. So OR gate. I mean, my bad. That's an OR gate. That's an AND gate. And that's an OR gate. Now that we know what logic gates there are, we just solve it. As simple as that. We just solve it. So the first thing that comes up here is A and B. A and B are being multiplied together. So we just multiply A and B together. So 0 times 0 equals 0. 0 times 0 equals 0. 0 times 0 equals 0. 0 times 1 equals 0. 0 times 1 equals 0. 0 times 1 equals 0. 1 times 0 equals 0. 1 times 1 equals 1. 1 times 1 equals 1. Then next on our list, we're adding B and C together. As you can see, B goes to the OR gate and C also goes to the OR gate. So we're adding B and C together. B plus C. So 0 plus 0 equals 0, 1 plus 0 equals 1, 1 plus 0 equals 1, 1 plus 1 equals 1 of something, 0 plus 0 equals 0, 1 plus 1 equals 1, 1 plus 1 equals 1, 1 plus 1 of something equals 1 of something. Then now we've finished C. Now the last part that remains, the first row here, is we're again multiplying B and no, not again. We're multiplying B and C together. As you can see, B is going into this AND gate, and C is also going into this AND gate. So let's multiply B and C. B, C. So 0 times 0 equals 0, 1 times 0 equals 0, 1 times 0 equals 0, 1 times 1 equals 1, 0 times 0 equals 0, 0 times 1 equals 0, 0 times 1 times 1 equals 1. Now, now that we have finished all of the ones here, all of the ones here, we can just cross them out to show that we have finished it. Now all we have left is the AND gate and the OR gate here. So basically, you can see that the OR gate, which adds B and C together, and the AND gate, which multiplies B and C together, are being multiplied again together here, and then later on being added to A and B. So we can leave the A and B out for this one here. We just multiply the B plus C and BC. And remember to use brackets to show which one to multiply first and which one to add first. Which one to add first? Let me show you. So you would add bracket across B and C. You would add a bracket across B and C to show that you add the B and C together first, and then you would add a bracket across B, the other B and C, to show that you multiply the B and C first before you multiply the addition before you multiply B plus C and the actual B and C multiplied. So this is what it would look like, as we have to multiply the B and C first, and then multiply with B plus C. That's why it's in brackets to show what to do first, what to do first, just like in like normal algebra. So let's continue with this. So now over here, what we do is we take the value of B plus C, which is this column right here, and we take the value of BC, which is this column right here, and we multiply them together, as the next gate that comes is the AND gate. So 0 times 0 equals 0, 1 times 0 equals 0, 1 times 0 equals 0, 1 times 1 equals 1, 0 times 0 equals 0, 1 times 0 equals 0, 1 times 0 equals 0, 1 times 1 equals 1. Let me erase this and write it again. not enough space. So 0 times 0 equals 0, 1 times 0 equals 0, 1 times 0 equals 0, 1, 0 times 0, 0, 0, 1. Now that we had this, we can now cross off this AND gate. This whole entire side is finished. This whole entire side is finished right here. This whole entire side is finished. All we have left is the OR gate. Now we just add this expression with A and B to get our final answer. I will show you how. I will show you it in the next slide. So now we're adding the bracket B plus 3, bracket BC, and the AB together. So it would look like A. It would look like A B plus bracket B plus C bracket B C. And you don't really have to bracket the B plus C and BC here like this because already the value for B plus C and BC is given to you over here. So all you would have to do is just copy this value onto here. So we don't really, I'm not really gonna put the bracket there. But if you want to, yeah, you can put the bracket there for you to see. But for me, I don't really need the bracket there. So now we just add them together. So we just go back and forth between the pages and see add them together. AB's first value is 0. B plus bracket this expression's first value here is 0. 0 plus 0 equals 0. The first value would be 0. Next would be again 0. And we continue doing this. Next would also be 0. Next one would be 1 because it's 1 plus 0. Next one would also be 0. The next two would be 0. And then the next two would be 1. And there you have it. This, so Q, so there you have it. Q, this equals to Q. This value right here equals to Q. And so there you have it. You're finished with the beginning of logic gates and how to use truth tables and what the logic gates actually are. In summary, you use the truth table and you look at the actual schematic over here. You look at the actual schematic over here, you read the schematic left to right and see which inputs are being multiplied or added together depending on the gate there is, depending on the logic gate there is, and you just plug it into the truth table to figure out what the last value what the last value here would be. And so in our case, the last value here is 000100011. And as I've said, it's 8 digits long. 1, 2, 3, 4, 5, 6, 7, 8. 8 digits long, and as we've done earlier, and as I showed you earlier, 2 to the power of 3 equals to 8. So we are correct. And you could plug this into a calculator, and you would see this is the correct answer as we have done the truth table correctly. Uh, the next part we're going to be learning is about Boolean algebra. What Boolean algebra basically is just how to take is just another way of solving these equations. Just like how we can solve this schematic by doing this truth table here and getting the answer through the truth table, which is right here. We could solve this equation. We could solve this equation and make it simpler. We can make it simpler. And to make it simpler, we need to do Boolean algebra. And to give you a brief overview of Boolean algebra, Boolean algebra is a set of laws and rules developed by computer scientists before us that we use to look at algebraic equations like the one above right here, and simplify it so we could draw out the schematic easier. Instead of the schematic looking like this, it would look much more similar. I mean, simpler. Instead of this looking more complex, this schematic would look much more simpler with the laws of Boolean algebra. Now, keep in mind, before we start Boolean algebra, you need the equation. You can either have the schematic or the actual equation itself. If you have the schematic, you have to draw it out. Hear this correctly. As I was explaining earlier at the end of teaching y'all truth tables and what each logic gate does and is, uh, Boolean algebra, as I previously already explained, is just the schematics written in equation form. So here, right here is a schematic, and this could be written in an equation form, and that would be known as a Boolean algebraic equation for this schematics. And basically, these algebraic equations can be very long and very confusing. In order to simplify them, we use Boolean algebra laws, and these laws allow us to simplify the Boolean algebra to a point where it's easy to understand and easy to draw. And these laws were created by George Boole, the man right over here, and another guy named De Morgan's theorem. But we will talk about De Morgan later on. Right now, we're going to focus on the laws created by George Boole, as his laws are more as his laws are more important right now. So just like mathematical algebra, how we use our math to solve the algebraic equation and make it simpler so we could plot it on a graph. Same thing applies here. We make the algebraic equation. I mean, we make the schematic equation even simpler so we can easily draw it as it's done here. Let's start. The first law we're going to be talking about is called identity law. Let's write it down right here. Identity law. What this law does is what this law shows you is that if there's a input like a and you add it with zero, it still equals to a. If there's an input like a and you add it with one, because a represents a value of one or zero, it would equal to one immediately, as in the OR gate you've seen. As in the OR gate you already seen that like one and zero, like one plus zero equals one. And if a is multiplied by one, it would still equal to a, because in the AND gate, you've already seen that when you multiply a number, on and on number together, it equals to one of the numbers, so it would be a. But if you were to multiply a number with zero, it would equal to zero. Here's what I mean: a plus one equals a, because one plus one equals one of something. That's why, as I've already explained in the OR gate. Sorry, it's identity laws because there's multiple. Then the next law is a plus, I mean, my bad, a times 1, which equals to a, because a holds a value and 1 times 1 equals to 1 of something. So a right here, as we've discussed in the AND gate. A plus 1 equals 1. So 1 equals 1. That is the next one. And the last one is a times 0 equals 0. This is what you have to look. This is what you have to remember when it comes to equations where there are zeros and ones, due to your solving So a lot of the times what happens is that when you're solving your equation, you'll end up sometimes having ones and zeros. And when you have ones and zeros, you're not supposed to really have them in your equation because you're only supposed to have the variables like A, B, and C, as you're only supposed to have the inputs in your actual equation. You use these identity laws to actually eliminate the one or zero here. So if it was A plus zero, it would still be A. A plus zero, it would still be A. It would still be A. But only if it's zero times A will it become zero, because as we know from multiplication, zero times anything would equal to zero. But as you can see here, A times 1 equals A plus 1 equals 1, A plus 1 equals A. They're literally alike. They're literally the same thing. They literally represent the same. As in the first two right here, you can see this is the same. And so this could equal to A times 1 equals A. I mean, equals 1 too. So this is one of the first laws. The second law we're going to be talking about is idempotent law right here. Idempotent law. What this law basically shows you is what to do if there's two of the same inputs slash variables added or multiplied together. It basically just shows you that if there's two of the same inputs slash variables being added together or multiplied together, it ends up being just one. It just ends up being the same variable. Here's what I mean. A plus A equals A. So if you're ever in a situation where you have A plus A, just know it simply becomes A. That's what I meant by if there's two variables or inputs with the same inputs, then just know you're adding them together would equal to same like input or variable, or if you're multiplying them together, they would equal the same variable or input. So same thing, A times A equals to A. So yeah, so basically what idempotent law does is it takes if there is a input and it is the same input, when you add or multiply it it will be the same. It will be the same input. As you can see here, that A plus A equals A and A times A equals A. Moving on to the next law, we have complementary law, if I'm correct. Yes, complement law. Complement law is basically like what it shows, like when there's a knot. So as we've learned a knotted the knot gate and how it looks like a knot can look like this or this. In this case, we'll be using this to for our knotted inputs. So complement law says that if there is a input and you add it with the same input but knotted, you're gonna get the value of 1. That's basically the complementary law. While if you're multiplying it, you're gonna get the value of 0. Why? Because because a naught represents 0 in this case, and multiplying something by 0 will make it 0. That's why. That's the complementary law, which deals with the knotted inputs. The next law we're going to be talking about is, so again, in summary, if you haven't understood the first time, um, in complement law, basically, if you have a knot, If you have a knotted A and a knotted A right here, right there, as you can see, right here, when you add it together, it would just equal to 1. And as I explained right over here, if you multiply, it equals 0. The next law we're going to be talking about is, just give me a second. The the next law we're going to be talking about is absorption law. So let me just write it down right here. Absorption law. What is the absorption law? Absorption law just deals with absorbing the actual just absorbing the variable, if absorbing an input or slash variable if there is a common variable between them. Here's what I mean. In this exact, here is A plus AB. Absorption law allows you to absorb the B because there is A and A common between in these two parts of the expression. The A, because the A and A are common here, and there's only two. Keep in note. You cannot do absorption if there is more than three parts, more than three inputs in the second in the second piece of uh, piece of expression. What this means is that what I mean by this is that if it wasn't A and B, if it was just something like A, B, C, even though A is common between A and A B C, I would not be able to do it. I would not be able to do it because it has three inputs. Because it has three inputs and not two, like here. That's what I mean by you cannot do absorption if there is more than three inputs in the second piece of expression. So A plus AB here would just equal to A. The B just gets absorbed. The B gets absorbed. Same thing here in this bracket. A plus bracket A plus B equals to A. As even in, as when as And the reason why is because in a later on law in distribution, when you distribute this and this over, it'll in the end equal to A plus AB, which directly just ends up becoming A. And so you see the reason why this expression here, A plus bracket A plus B still equals to A, is because if I were to open up the brackets, which I will explain to you later on, if I were to open up the brackets right here, it would look like A plus A B, and I would use the identity I would use the idempotent law, and I would be able to tell you that A and A just equals to A. So if you were to open up the brackets, it would just be A plus AB. And so after that, we can cross out the b with the absorption law and equals to a. So a plus ab indirectly is just a plus ab. A plus, I mean, a plus bracket ab indirectly is just a plus ab. That's why both of them are the same thing. So if you see it in the form of a plus ab, you don't even have to open up the brackets. All you have to do is directly from this expression, you can easily just turn it into a. Now that you've seen it for yourself in the absorption law. The next law we're going to be talking about is involution law. Let's type it right here. Involution law. This is one of the, I say, the simplest laws out there. Involution law just say if there's something double knotted, like a double knotted, it just equals to a. The reason why is that when something is double knotted, it just goes back to its original position. So let's make a truth table for this, shall we? A, then a knot, then a double knot. Let's make this 0, 1. As you can see in the first knot, it gets reversed, 1, 0. But in the second knot, it again gets reversed. This value and this value is the same. And as you can see here, A and A double knot is basically the same thing. And because it's basically the same thing, it would just be A. Another example of this is like if there's A 4 knots, it would still equal to A as long as there is an even number of knots on the thing. Because if we were to do this with the truth table out, A knot, A double knot, A triple knot, A you would see that in the end every single one of these every single one with the even number of knots ends up being the same value as a itself. As you can see, every one of these knots, every input with a even number of knots ends up having a involu ends up having the same value as a by itself. Here, let me show you. I'll just put it up here. So let me show you. 0, 1. In the first knot, it would just be turned to 1 and 0. But in the even number knot right over here, as there's two knots, it would be 0, 1. Same as the first one. In the next knot, it would be 1, 0. But in the next even numbered knot, which is 4 number of knots, it becomes 0, 1 again. Keep in mind that 0, 1 just represents 0 and 1. So I'm literally just doing 2 to the power of 2, which means 2 combinations. Which means 2. That's why I'm using it. So as you can see, this just becomes the same, 0 and 1. This just becomes the same, 0 and 1. And as you can see, every single even numbered amount of knots just ends up having the same value as A. So A even knotted equals to A. That's what these two knots mean overhead. Equals to A. The next law I would like to talk about is the simplification law. My bad. Simplification law. I'll do it on the next slide. Simplification law is basically the same thing as as our absorption law, except with knotted inputs. Let me show you. So it's in the same format. It's in the same format. A plus AB. So it's almost. I mean, the simplification law is very similar. Is law is the same thing except it uses knotted inputs. So what I yeah that's correct. What I mean by this is, uh, when it looks very similar. So you have something like A plus A underscore B. This would equal to A plus B. As you can see, this right here is very similar to our absorption law. Except it just has a knotted input here. And the only difference is instead of just A being there, there's B added. Same thing, same thing, except just a different law. Same thing. There's the one with the brackets too. So A bracket, A plus bracket, A not plus B, which just results in A plus B. So same answer, same way it's written as absorption law, except there is knotted inputs, and so instead of there being the single A there, just like the absorption law, there's again a B there as well. And remember, just like the absorption law, you cannot use this law if there's more than three inputs here. If there's more than three inputs, well, you can just remember that. Well, just remember that then. If there's more than three inputs here, and there needs to only be one input on, and then only needs to be one input on this side, and there cannot be more than two inputs on this side. That's how it works. So that is our simplification law. The next law we're going to be talking about are the commutative and associative laws. The commutative laws is very simple. It just talks about whether you rearrange it A plus B or B plus A, it will still equal the same thing. Here's what I mean. Just like in normal math. Commutative law. So just like in math, how you would write something like 2 plus 1, or what, it doesn't matter how you write it. Like you could write it as 2 plus 1 with the 2 in front, or the 1 plus 2 with the 1 in front. It would still be the same. It would still be the same answer, 3. Same law applies in Boolean algebra. A plus B still equals to B plus A, regardless of which way it goes, regardless of the positions of the inputs. Same thing applies for multiplication. A times B equals B times A. So it doesn't matter which position the the inputs are in. The next law I would like to talk about is associative law. Associative law is very similar to the commutative law. So, sorry, that's not how you spell it. Uh, so, associative law. Basically, the associative law is the same thing, except it shows you what it looks like in brackets. So regardless of what's inside or outside the bracket, unlike our regular algebraic math, regardless of what's inside or outside the bracket, it'll still be the same. It'll still be the same. It'll still be the same. Here's the first example. Sorry, wrong color. Okay, a plus a plus b bracket times no, I mean plus c equals to a plus b plus c. Same thing for multiplication. A times b times a, times c equals to a times b times c. Keep in mind, just like absorption law, the actual expression should only have either plus or multiplication in it in order to use it. What I mean by this is if it was something like, here, let me move this. If it was something like a plus b times c, you would not be able to do this. Or if it was something like a times b plus c, again, you would not be able to do this. They all need to have the same logic gates. So this needs to be plus and this also needs to be plus. This needs to be multiplication and this also needs to be multiplication. So as you can see, that is the associative law. The next and final one of the main laws I would like to talk about is the distributive law. Let me write that down right here. The distributive law, like math, is like math is like a then b plus c. Like math just opens up the bracket. So just like how in math we open up the bracket for equation, here it's similar to math, and you open up the bracket. So it just become ab, as you when you're opening the bracket you multiply each one. Ab plus ac. Unlike math though, unlike math, when it's a plus bc, when it's something like a plus bc, you could actually write it like ab plus ac. So when you expand it, so so when you expand it, it will be a plus bc, the same. So the few laws that I've talked about are the main laws on Boolean algebra. There's one last law to cover. And this law is known as the De Morgan's theorem. Is the De Morgan's theorem. In the De Morgan's theorem, so let's first type it out. De Morgan's theorem. For the De Morgan's theory, the De Morgan's theory looks something like this: A plus B equals A times B, or A times B equals A B. The reason why we want to separate this is because if we don't separate it, we won't be able to use the other laws. We won't be able to use the other laws that we've learned. In order to simplify an equation, you need to separate the knotted gates into single knotted gates. And as you can see, in order to separate them, if they're adding, we just do the opposite of adding, multiplication. If they're multiplying, we just do the opposite of multiplying, which is addition, and these will separate the inputs, the or slash yeah, the inputs into a single inputs like this, and so you'll be able to solve your equation. But you may be solve your, yeah, Boolean algebra. But you may be wondering, how does this theorem exactly work? This theorem works because De Morgan, the guy who created this theorem, has seen that when you have a negative a and you have a negative b, it actually equals to the reversed negative a and b. What I mean by this is what I mean by this is that as you can look here on the newly added tables, a plus b knotted equals to a times b reversed. As you can see here, a plus b is knotted. That's why when you do 1 plus 0 and 1 plus 0 and 1 plus 1, it all equals to 0. But when it's 0 plus 0, it equals to 1. As you can see here, a plus b knotted together is equal to the reversed of a times b, because as you can see here, the zero is at the bottom, then it counts. Zero is at the bottom, and it counts from zero all the way to 3 from bottom up, not the usual way, of going from top to bottom. And so in that way, you can see that the knotted version of a plus b, which is 1000, is equal to this, to the inversed a times b, as a and b here are inversed, so that 0 is at the bottom and 1 is at the top, and it equals to the same thing. So that is why when we broke this up right over here, so the whole knotted a plus b into the single a and the single b naught, it worked because when we opened these brackets up, when we open these I mean, not brackets, when we open this knot up, we created this right over here. And so in because of this phenomenon of a plus b knotted equaling to a times b inversed, we were able to open the brackets up, as I said, and in that way a naught times b naught equals to a b knotted together, due to this one single phenomenon. Same thing over here for this one, because the reason why we can open up the a and b knotted into a naught plus b naught is because a and b knotted, as you can see here, a and b is knotted equal, just like the first theorem, a and b knotted equals to a plus b reversed. As you can see, just like in the first theorem, here a and b is reversed, so 0 starts at the bottom and it goes to 3. Instead of starting at the top and going to bottom, we're starting at the bottom and going to top. So a and b is actually a times b knotted is actually equal to a plus b inverted. That is why when we break up a and b here, and we make it a naught plus b naught, it equals the same value, because a naught plus b naught just means that it's inverted now. It just means that it's inverted now, but due to the phenomenon, as I said, makes it equal the same thing. So in that way, De Morgan's theory works out. So you can use De Morgan's theory to break up blocks of knotted text like a plus b naught or a times b naught, and you could break them up and turn them into this. You break them up and turn it into separate things. So plus becomes multiplication, multiplication becomes plus, and it becomes separate. Not because you are actually just inverting the value, inverting the value from the not, so it would equal the same thing. And from there on, you can actually solve for the actual equation, because when it's knotted all together here, you cannot really solve for anything with the previous Boolean laws I've given you. So next, so these are all of the laws. So all of the laws that I've showed you, all of the laws that I've showed you, all of the laws that I've showed you, uh, help you help you simplify Boolean algebra. Help you simplify Boolean algebra. So with being said, all of these laws can help you simplify a Boolean algebra. Here I'll be showing you an example. I'll be showing you an example. Here I'll give you a random Boolean algebra, and I will show you how to solve it. So the random Boolean algebra that I want to use here is y equals ab plus ab. Here, let me show it to you. Y equals ab plus a together knotted, then b not. The schematic for this would look like, as you can see here, here's the schematic for the equation over here. Basically, we use the laws that we have learned, and the laws that we have learned, including De Morgan's law, absorption law, every single law that we have learned, and we use those laws to solve for this. What I mean by that is, depending on what variables here are present, no, what inputs here are present, and how they're presented to us, it is your job to figure out what laws you can use to your advantage to make this equation simpler. Let me show you an example. In order to make this equation simpler, the first law that comes to my mind is De Morgan's theorem. And the reason why De Morgan's theorem comes to my mind is because of this value right here. As you can see, A and B are double knotted together. And we could use De Morgan's theorem to spread them apart. So now we're using De Morgan's theorem. So as we've learned in De Morgan's theorem, because it's multiplication, we end up using addition between them, and that divides them. So we could just write De Morgan's, and that becomes a b plus a naught plus b double naught. Now we use our brain and we figure out what law we can use next. The next law that comes to our mind is the involution law. So after we did the De Morgan's theorem, we were able to simplify the equation, and we were able to use other laws. And now the next law is involution law. So a b knotted just becomes a naught plus b no knots, because remember the involution law. The next law that comes is simplification law. I'm just gonna write simple for simplification. What this does is, it takes, in simplification law, we can take, in simplification law, it's the same thing as absorption, if you've remembered, and but it involves knots. As you can see here, this looks exactly the same as the statement in absorption law, except there is a not over a, which makes it part of the simplification law. And if you've remembered, we know that the simplification law allows us to absorb this a here, and so in the end it just becomes a naught plus b, as we've absorbed the a, as simplification is basically just like absorption but with knots. The final answer, which is y, equals to a naught plus b. As you can see, depending on whatever was presented to me in the first place, through the equation, I remembered my laws, and I was able to use my brain to figure out what laws I could use to solve it, which is exactly what you just do. So on a test or a sheet or paper, you will be given the laws, but what's up to you is to figure out where and when to use the laws. So you don't have to memorize the laws. You just have to know where, or when to use the laws. Like like if you didn't know like how to use the simplification law, you would have instead used the absorption law right here. But because we have learned how to use the simplification and absorption law, we know that here we don't use absorption law, but we use simplification law. And this marks the end of Boolean algebra. So if for Boolean algebra, you just have to know what the different laws are. You just have to know what the different laws are, and how we can use the different laws, and how we can use the different laws to simplify a Boolean equation such as this. Finally, the last part about our logic gates lesson is half adders and full adders. So half adders and full adders are just another way to add binary numbers with logic gates. So as you have learned, when it comes to binary numbers, when you were to add something together, like 1 plus 0, it would equal 1 because there is no carry. When you're adding binary numbers together, there's something called a carry, and a sum. Just like in normal math, a carry means it gets carried over to the next column, while the sum is the actual number that's put down. For instance, if I were to write something like 1, 1, 1, 1 plus 1, 0, as you've learned, there is no carry in the first part, so 1 plus 0 equals 1. But because there's an even number of ones here, this 1 is actually a 0, and it gets carried up to here, depending on the amount of groups. There's only one group here, so it gets carried up as you've learned. So now there's another group here, so it's another 0, and the 1 gets carried over again. And so because there's no value here, we immediately think of it as a 0, and so the answer is 1001. As you can see, the sum here is the actual addition between them. And in the first row, the sum here is 1. In the second row, the sum here is 0. The third row, the sum here is 0. But the fourth row, 1 plus 0 equals 1. So the sum here is 4. And the carry on is this value that's being carried on. So basically, half adders and full adders are another way of adding binary numbers without actually having to add the numbers together. You could use the logic gates that we have learned to create how do I yeah, yeah. So basically, half adders and full adders allow you to figure out how to add two numbers or values together without actually having to go through the actual process of adding them. So instead of going through this process, you could just use the half adders and full adders to do it for you. And I will explain to you how these half adders and full adders work. I was saying, in order to understand this, you have to see what it looks like on an actual truth table. So we're for this truth table, we're just counting from zero to 3 for two inputs, one of the most basic truth tables there is. And if you look closely here, the sum for the values of 0 plus 0, then 1 plus 0, then 1 plus 0, then 1 plus 1 uh, is equal to the XOR gate. The sum here is equal to the XOR gate. While the for the carry, where as you've learned earlier, and as I've reviewed with you earlier in the previous slide over here, the carry, there's only one carry here, which is when it comes to 1 plus 1. But the carry also resembles a AND gate. So basically, what we can conclude from here is that the sum of inputs are actually the XOR gate, while the carry of the inputs are actually just the AND gate. And so due to this phenomenon, that when we're adding numbers together, as you've seen over here, as we're adding 0, 1, 2, and 3. This is a 2 to the power of 2 4 combination truth table, which is one of the most basic truth tables. That's why we're using this, to show that all other like additions are based off of this. You can see here that the most basic additions are literally just XOR gate and AND gate. So the sum row represents the XOR gate, and the AND gate represents the carry column represents the AND gate. So due to this very interesting phenomenon, we could actually use logic gates that we've learned to add them together. We could use the AND gate and XOR gate in a way that instead of actually manually adding the binary numbers together like this over here, we could just plug them into the half to the XOR and AND gate. So we could just plug them into the XOR and AND gate to actually just through the logic gates actually do the addition, so we can get the value of the sum and the carry. Now here's how it's done. So there's something called a half adder and full adder. Let me show you. It's a half adder, and as I was saying earlier, that in like we could use the AND and XOR gate to actually, instead of manually just uh, adding them together, we could just use the logic gates to add them together. That's exactly what we're going to be doing here. So you see this schematic that you see over here is actually called, what as I said earlier, is a half adder, and this half adder allows you to manually add two inputs together. And what exactly do I mean by that? Instead of actually just going manually here and doing 0 plus 0 equals 0, then 1 plus 0 uh, equals 1 as the sum. Then once we come to 1 plus 1, we would have to do 1, then carry over the sum, and it would equal to 1 0, and it will equal to 1 0. Instead of doing all of that, we could just plug the a and b value into the schematic. And the reason why the schematic works is, as I've said earlier, the carry column is actually an AND gate. If you look at it, it looks exactly like an AND gate. The values are just like an AND gate. 0 times 0 equals 0. 0 times 1 equals 0. 1 times 0 equals 0. 1 times 1 equals 1. And the sum column, it looks like an XOR gate. One or the other. 0, 0, one or the other. One or the other. One or the other. One or the other. So so as you can see here, if we were to plug in A and B here, we would get the correct sum and the correct value to give us the correct answer of adding the two binary numbers together. As the XOR gate would just lead us to the sum value, while the carry would just give us the carry value. And we could just plug them into a reader which tells us the value. So let me just show you an example of this. Here, let me show you. If I were to plug in one here and one here, the answer I should get is 1 0, as shown over here. And the answer you will get is 1 0, because the XOR gate will represent the sum value over here, and the AND gate will represent the carry value over here, creating the 1 0. Let's show you how it's done. So one value here is here, one value here. So first, the two 1 values come together here at the AND gate, and it becomes XOR. So let's draw this out. So A plus B. That's currently what's happening over here. And because A has the value of 1 and B has the value of 1, and it's one or the other, what will the answer be? Well, if you remember what we did in our XOR gate, when there's 1 and 1 and it's an XOR gate, it does one or the other, the value is 0. So immediately we get our sum equals to 0. And then the next part is the carry part. Next part is the carry part, right over here. Right over here. In the carry part, it'll represent this column, this row over here. Column, this column over here. And now we're going to multiply the two ones together. 1 times 1 equals, well, you guessed it correct, 1. And so because the carry isn't going into any other adder, as when I show you what full adders are, you will see that the carry gets moved on to the next adder. What I mean by this is that as we have done in normal by adding binary equations, the carry keeps getting moved over, let's just say there's 1 and 1 here and 1 and 0 here. The carry gets moved over, does it not? That's the whole purpose of a carry, to move a value over to the next row. That is exactly why we have a carry here, in which if there is nothing to move over and it's 0, like in our case, if you were to add 1 and 1, it would be 0. There's nothing over here, so the carry would just plug into the sum, and it would just give you 1 0. And so in our case, we don't have anything to plug the carry into. So in our case, when we get 1, we just plug it in with the sum. So the answer equals to 1 0, as the sum here equals to 0, and the carry here equals to 1 due to the AND gate. And so in the end, we get 1 0 as our answer. And if we were to go back to our original table right here, what does it say? 1 0 is the answer. 1 0 is the answer. So that's how you do half adders. Half adders allow us to add two digit to add like they allow us to add the first two digits ever. So when you're first starting to add something, you would use a half adder to first add the first two digits together. As when you first start adding something together, you don't just already have a carry. You don't. So there's no carry coming in. You first have to add the two digits together to get a carry, and then the carry starts moving over. And when the carry starts moving over, like over here, that's when we get a full adder. Now here's what a full adder is. A full adders come in, and as you can see here, as I explained earlier, when we're adding something, we have to first add the first two digits together, yeah, or the first three digits together. But basically, we have to add the first few digits together to first get a carry, because when you first start adding a number like this, you won't immediately have a carry. Just that's simple mathematics. That's simple logic. You won't immediately have a carry. So there is no carry coming into this. There is no carry coming into this part. The carry comes in once you're finished with this part. Then the carry comes. And that is why we use the half adder first, as the half adder does not have any input for carry. See, it has no input coming in from another carry here. It has nothing. The half adder allows us to start adding the two binary digits together. Like in this answer that I've showed you, the half adder allows us to first add these together, and then we can start coming into this. And when we start coming into the other rows with the carries, that's when the full adder comes in. Now, as you see here, the full adder is actually just another half adder. Look, this is the half adder that we've all discussed. This is the half adder that we've first discussed. After the half adder is done, meaning we have finished adding the first two digits. Sorry, it's a little messy. 1 second. So now that we've done the half adder, meaning we've finished adding the first two digits, which would be this, we move on to the full adder. As in the full adder, there's something called the C input, which means a carry input. And so just like how in regular adding of the binary, we carry the input over, we use the half adder we use the full adder after the half adder, because after we've added the two digits together to get a carry, we can now move the carry on forward. And so when we move the carry on forward, the carry goes through here, and it gets combined with the rest of the input and the rest of the question. So in this question, 1 1 1 1 plus 1 0 1, after we've added the carry together, after we've added these two 1 and 1 together, and we've got a carry here, the carry comes here, and now we are supposed to add them together too, right? Here, as I've explained earlier, the XOR gate represents the sums, and the carry gate and the AND gate represents the carry gate. The CN actually goes to the XOR gate. as that's direct as the carry gate from here will directly result in us in our sum over here. So once the carry goes inside here, it gets added to or the yeah it gets added to the first value, the sum value over here from A and B together, and then that's how you get your sum. So this whole part over here is how you get your sum. Is how you get your sum. And as we have learned, as we know earlier too, when we're doing questions like this, we're all, again gonna have a carry too. So in this example, 110. So in this 110, we have now finished the first part, which is this part over here, 011. And now that we have the sum through this part, we now have the sum. So this the sum of this would be 11. There's two values, so this would be 0. Would be 0. But we had the sum now. But where would the carry go? As now we know that there is another pair. As we now know that there is another carry here. So there's another pair here. So there would be a carry over right over here, 1. So how would it know? Well, guess what? As I've explained earlier, the AND gate all deals with that. The AND gate all deals with that. So after the sum is calculated right over here, with the XOR gates, as the XOR value XOR truth tables represent the sum column, as we've explained earlier. Now the AND gates start working together to create the next and to create the carry out, to create the carry out that will go into another carry to go into another full adder. So what I mean by this is that just like how there is a 1 and 1 here, and it's being carried over here, so it could again be calculated together. Same rule applies here. The what the value from A and B from the XOR gate over here, it gets put into an AND gate, and this carry in again also the carry in also gets put into an AND gate, and then whatever values from there is in A and B, just like a half adder, gets put into an AND gate, and they all get added together. What this ensures is that whatever carry we have, what this ensures is that whatever carry we have from 1 and 1 right over here gets added together with the previous carries, if there were any previous carries. Because sometimes you might get questions like 111, 111, 111, 111. Let's just say, and you're gonna have two pairs here. You're gonna have two pairs here, and you're gonna have end up having two carries. And in order to make sure that and if they don't fit, and if they continue getting carried over to the next row, in order to make sure they get continued carried to the next row, the full adder multiplies both the carry in value and the value of A and B from the XOR gate alongside. It adds the carry in value from it adds the carry in, and it also adds the carry value from the A and B from itself by itself from here together to create the carry out, which will be the carry in for the next full adder. And so in this way, your half adder is the first is the your half adder is the first like set of logic gates that like control adding the first two digits in your or first few digits first digits in the first column, like 1 plus 10111. It controls adding the first digits in the first column, while the full adder deals with adding the rest of the numbers, deals with adding the rest of the numbers. And it does this by multiplying all of the carries together by multiplying the carry in, taking AB's carry, and then taking the XOR value from AB and multiplying them and adding them all together here to create a single carry value that will go into the next row, and that next row will be able to do the same thing again as another full adder is added. So depending on how many rows there are, you'll have to add that many full adders. This is what I mean. So for the question we're doing is one. Let me just use a sticker brush for this. 101 plus 111. Let's just say that's the question we're doing. Yeah. So here you would need one. You always you're gonna need a half adder in front, because As I explained earlier, the half adder is what first adds this together. Without a half adder, you would not be able to get a carry in over here, and so you would not be able. The full adder would not be able to work, as I explained. As I explained. So depending on how many rows there are, that is how much. That is how much like that is how much full adders you have. So right now there's two rows here, right? So this whole entire full adder, this whole entire full adder represents this row, as whatever sum we get here will be the sum of this row right here, and whatever carry we get here will be this carry of will be the carry of this row. And here, because we have two more columns after the first one, we need one more of this. We need one more. We need one more full adder so we could actually do the carry. In that way, listen to this clearly. Every single single full adder talks about one row. So every single full adder just deals with one row. So while the half adder deals with the first row, which is this row right here, every single full adder deals with a single row. So one full adder cannot just take in the whole entire rest of the uh, like question. But but sorry, one sec. But one full adder takes in the one row after the first row, which is controlled by the half adder. So whatever the sum of this row will be is actually done over here through these. And so that's where the sum will be. So this sum comes from here, while the carry comes from adding, as I said earlier, multiplying the two carry in and the XOR gate, and adding uh the A and B multiplied from over here to here. In that way, every single half adder represents one single every single half adder represents like one single row. So in this question, there is two more rows after the first row, which is controlled by the half adder. So you would need one more full adder like this. And basically in this full adder, you would just use the carry. And this is where it would be. So let me show you what it would look like. For the next row, which is this one, you would need another half adder, and the carry from here would come down here. As in normal adding, we bring the carry from one row to another. The carry from here, which is the carry of this whole row right here, will come over and come back into here, which will create the carry for this row and result to our sum. And if there is a carry from this row, it'll result to a carry, in which it'll give us our answer. In that way, the half adder, it represents the first column of adding, as you need a half adder to first add and get the carry value, and the full adders each represent the rest of the rows for carry. And each half adder next represents each full adder next represents each the rest of the rows. So in this way, every single full adder represents the row, a single row. And if there is no more rows after that, the carry will automatically just go to the sum, which will result to the answer right over here. So in that way, you use again, for summary, the half adders are used for the first row. Sorry, it's a little messy. Are used for the first row. Then the full adders after that represent each row afterwards. As each row afterwards has one full adder in it, and it calculates the carry for. And this is how a full adder looks like, and it calculates the carry for you, and takes the carry on towards the next row, as this is the carry out, and that goes to the carry in, as I've explained earlier. And if there is no more rows after that, the carry just gets turned into a sum, and that's how you get your answer. So instead of actually doing it manually, you could use the logic gates like this, and it gives you the value. And remember here that just like how the carry goes in here, from the half adder, the carry goes out from here to here. So the carry goes here, then the carry goes here. It continues carrying over depending on how many rows there are. For example, let me show you. Let's just do a simple one like 1, 1 plus 1, 1. Through normal addition, this would just be 1, 1, 1 row, so 0, then 1 over here, 1 over here, but this would again be 1 and 1. So that's how we would do it through normal ones, as there's a thing, as you've learned earlier, as there's 1 over here, then there's a carry and that's a pair, and it's not uneven, so there's 1 here, and then there's nothing here, so the carry just becomes the sum, 1 here, 1 here. Instead of doing this way, we can use the logic gates. So we know that 1 1 plus 1 1 has 2 rows, and the first row will always be a half adder. The first row will always be a half adder. So we add a half adder onto this. For these parts, you will have to memorize. You will have to memorize that the half adder is you'll have to memorize what a half adder looks like. But here I'll just give it to you. So this is what a half adder would look like. So you would know that the value for A is 1. The value for, let me just do it so you can see it. The value for A is 1 and the value for B is 1. So, and you know that there's only one more row after this, and because there's only one more row after this, we would only need one more schematic, which would be a full adder. As remember, only the first row is a half adder, and the rows after that are all full adders. And keep in mind, and remember, the carry goes here to here. And so without actually doing it, we could just plug it in. So we know that again, A and B is 1 here. So now we just solve for it. So 1 and 1 equals 1 or the other. So the first one will be 1 or the other, which will be 0. So we know the first sum for this value due to here is 0. And then we just add them, multiply them together, and so we know the first carry is 1. And if we do it manually, we would know we're on the right track, because if we were to do it manually, this is even, so it would be 0, and we get 1 carry on. See, 1 carry on and 0 as the sum. So we're on the correct track. Now we have a carry on here. So we would just find the sum for this one first. So 1 and 1, 1 or the other, 0, 0. Then the carry in is brought in here, 1 or the other, 1. So we would know that the value here is 1. As if you solve for the logic gates, here, when the 1 and 1 go through this XOR gate, it becomes 0. But when it goes through this other XOR gate, which comes in with the carry in from here, it would become 1 again. So the sum is 1. So we would know 1 automatically comes here. And now we would need to know how much there is carries. And if we were to do through the logic gates, like multiply them right over here, and then multiply them right over here, you would know that the carry is also we do 1, then 1. So this would be 0, 0 times 1, 0. This would be 0, then 0. Then this would be 1. So 1 plus 0 equals 1. So we would know the carry here is 1. And we're correct, because as you can see here, this is the carry from the previous row, and we have one pair, but we have, as we would know there's only one value here, so we are correct, as in the sum value we got 1, and the correct answer here is 1, as there's an uneven number of ones here, and we would know that 1 gets carried over as there's one pair here. And as you can see, once we've done the actual logic gates, we've seen that a carry is also 1, so we are correct. And because there's nothing else to carry it over in, as there is no more rows here, it's only 2 rows, the carry just becomes a sum. And so the answer would be the 0 comes here, the 1 comes here, and the carry just comes here. So the answer would be 1 1 0 according to this. While according to the schematics, while the same answer would apply here. There's no number here, it's just 0, so 1 plus 0 equals 1. So we get the same answer, 1 1 0. And that is how half adders and full adders work. Half adders deal with the first column, while full adders deal with the rest of the columns, and the carries continue getting moved on and moved on in the full adders, just like a normal equation, until there isn't anything to move it on towards. And when there isn't anything to move it on towards, that just becomes the carry just becomes a sum. So to clean it up, so to clean it up for you, to clean it up for you, the answer here would be 1 1 plus 1 1 equals 0 1 1, one pair here, one carry here, then one more pair here, one more carry here, which results to the 1 here. Same thing here, 1 1. This ends up being 0 due to the XOR gate. This ends up being 1. This 1 is carried over here. This becomes 1 1 1, and then the B and A and B through the XOR gate becomes 0, but again through the XOR gate become 1. So the sum here is 1. So we already know two sums. So the first sum is 0, and the second sum is 1. Second sum is 1. And then after that, we just figure out the next carry, and the next carry would be just taking the 0, multiplying it with the carry in over here, which makes it a 0, then adding it with the carry over here, which is a 1, and so 1 plus 0 equals 1. And because there isn't a carry, it just comes to the sum. It just comes to the sum. So it's 1 1 0. In that way, uh, this through this you get the correct answer, and this you get the correct answer. So this is just another way of adding binary numbers, as I've just said. But usually what happens is that this gets a little messy. Like as you've seen, this gets a little messy. So there's an easier way to show this diagram, to show the schematic. There's an easier way to show the schematic, and I'm about to show you. Instead of drawing it in the usual way that I've shown you here, we're just gonna draw it like this. Drawing it like the other ones right here. We could just draw it like this. And the same thing applies here. Instead of actually drawing the logic gates out, like instead of actually drawing this XOR gate out, then this AND gate out, then all of these gates out, instead of actually drawing that, we could just write it like this. So the half adder would just look like this. This is where the value is. So for 1 1 plus 1 1, this is where the value is, and the sum would be again, the sum would be 0, and then the C would be 1, the C would be 1, and then again the carry in just goes into here, and this would be 1 1 1, in which the carry would be 1 and the sum would be 1. So you would still need to know like how the logic gates are placed. Like you would still need to know that this is how a half adder looks like with an XOR gate here and the AND gate here, and this this is how a full adder looks like with the XOR gate, XOR here, then sum, then the and OR gate, then carry. But instead of drawing it or writing it out like this, you could just write it out like this. You could just write it out like this, and it's much simpler in that way. Since now when you fully remember what a half adder looks like and a full adder looks like, you'll be able to do it in your head just like me, just like me. So the answer would again be the same. So the first sum here is 0, the sum here is 1, and because there's nothing to carry on, this just becomes a sum. So this becomes 1 1 1 0, and again if we do it, it becomes 1 1 0, and that's it. That's how you do half adders and full adders, and that's the end of logic gates lesson. Thank you. Lesson on logic gates unit. Before we start, here's the table of contents. Here's the timestamp and here's the content. From 0 to 1 hour and 9 minutes 50 seconds, it talks about truth tables and functions of each logic gate. From 1 hour 9 minutes 52 seconds to 1 hour 49 minutes 58 seconds, it talks about Boolean algebra. And lastly, from 1 hour 50 minutes to 2 hours 26 minutes 58 seconds, it talks about half adders and full adders.